Morning, everybody. Give another minute or so for everyone to join. Okay, looks like we have quite a few people in and ready. So I run recitations probably a little bit different than you might be used to. I like it to be student centered, um, where I take questions that you guys have. If you guys want to cover a topic that we've talked about that you just want some clarification or want to do some practice problems with it, that's what I will always ask first. What questions do you have? What topics do you want to review? From there, I'm always happy to just make up practice problems, but I can make up practice problems in something you've already mastered. So I'd much rather take ideas and questions that you guys have and go from there. So if you throw anything you want to discuss in the chat, or if you're brave enough to unmute and say it, um, let's start with that. I will open up the chat. Oh, I hear my cat. I might have to kick her out. Let me get the document camera pulled up. For those of you just joining, quick recap. I like to have it be recitations be relatively student centered in the fact that I can make up practice problems all day long, no problem, but I'd rather make up practice problems that you guys want to talk about or talk about topics that you guys want. So I saw resonance. Let's talk about resonance. Something else I want to say too, because these recitations are recorded, you are always welcome to watch the other sections' recitations. Because of how I run recitations, they might have different questions and review different things than we talk about here. The more practice, the better. So feel free to watch their recitation videos as well. All right. Let me get the document camera shared. Okay, so it should be there, and I pull up the chat over here. Resonance. Resonance, yes. Everyone's absolute favorite thing because it's so easy to do. Being sarcastic, of course. It is a little bit tricky at first, but let's look at some examples and hopefully that'll help clarify what's going on. So let's look at some resonance structures. Let's start out relatively, well, let's just start. I'm going to use line angle because we did talk about that yesterday, but I'm happy to take questions about that as we get going. So say I have this structure here. That negative charge right now, oh, that's not the right place for it. I apologize. Yeah, we're going to want it right here. And so the reason why it wouldn't work here is because if we try to turn that negative charge, which is really, let me refocus this. If we try to turn that negative charge into a bond, which is one of the most common forms of resonance we do, it would put a double bond here because we can only move one bond at a time, which would then put too many bonds here. So by putting the negative charge here, we're now able to do some resonance and interact with this pi bond. We'll talk more about pi bonds today, but it's just a double bond. So this double bond represents electrons. Remember, electrons carry a negative charge. So we can move this right there. We can turn those electrons from being held on this carbon to being shared between these two carbons to form a double bond. However, when we do that, this carbon here has 1, 2, 3. Wait, it only has 3 bonds? No, it does have 4 bonds. Remember, with line angle, if there's not a charge, we assume it has a full octet, therefore there's what's called an implied hydrogen. So from there, if we try to add another bond to a carbon that already has 4 bonds, that's not going to work. So to help compensate for that, we can take this bond and turn it into a lone pair on that carbon. So this is more of a two-step resonance. So when we go to draw our product, we draw out the base first. So 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. Our negative charge was here. We now shared it between these 2 carbons. So now it has a pi bond. From there, this was a pi bond, but it's now turned into a lone pair. Feel free to draw lone pairs. I just save a little bit of time and just draw the negative charge, but if you want to draw them both, there's nothing wrong with that. So as we push this here, that would have been too many bonds here. If you need to draw on your hydrogens at the start, nothing wrong with that. So now it has 1, 2, 3, 4 bonds. Now this has a lone pair. So instead of this carbon here carrying this negative charge, which I kind of referred to yesterday as this big giant refrigerator, now the refrigerator is being shared between 2 carbons. So it's a lot easier to manage. So I'll also talk about resonance hybrids real quick. So what if I want to show both of these things in one image? We can do what's called a resonance hybrid. Resonance hybrid, where we try to show both at once. So how we do that, wherever there's a single bond, we want to draw that. In our example, we have 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons. We don't need to draw hydrogens because remember we're in line angle formula. From there, wherever there's, you can either think about charges first or you can think about bonds first. Wherever there is sometimes a pi bond, so sometimes a double bond's here, sometimes a double bond here, we can draw a dotted line. And then because those electrons are being shared, it doesn't get a full negative here and here. Really, they're more of a half, but I'm not going to make you do the math as long as you show a partial negative on both of those carbons. So remember, at its core, resonance, what resonance is and why we do it, is moving electrons around to delocalize a charge. It doesn't matter if that charge is positive or negative. We are just moving a charge around via electrons within one molecule to help disperse that charge. Instead of one person carrying the refrigerator, we can have 2 friends carrying the refrigerator, and that makes it a lot easier. In this case, it makes it a lot more stable. Any questions with that? If there's no questions, would you guys like another example? Yes, okay. We can do examples of resonance the entire time if you guys want. This is your time. Okay, let's try. Let's try with some heteroatoms. So I'm going to put a nitrogen here. Then let's do. Whoever's playing music, please either turn off the music or mute yourself. So let's try this out. This one is just a 1-step. So I want a resonance structure for this compound. Give you a second to try it, think about it, and then we'll do it together. So the first thing that I think about is that nitrogen doesn't have a charge. When I give you resonance structures, I have to include all charges. So if it doesn't have a charge, what is likely on this nitrogen that's not currently being shown?
Lone pair.
Lone pair. Perfect. Yeah. So with line angle formula, I don't have to show lone pair. You don't have to either. However, as you're first learning, it's totally okay to draw that in, and I recommend it. So now we have a lone pair. Remember, when we draw these arrows, we think we want to go from electron rich to electron deficient. So with that in mind, try drawing out what the resonance structure would look like. So if we move our electrons from electron rich, where there is extra electrons or electrons that can be shared, to electron deficient, remember positive charge is whatever atom it's attached to, it's screaming out, help me, I don't have a full octet, I want some electrons. We can turn that lone pair and share it between the carbon that needs more electrons and the nitrogen to form a double bond. However, I'm not done. What am I missing from this resonance structure? Yesterday we talked about conservation of, does anyone remember? Positive charge, conservation of charge, yes. So again, this is our formal charge stuff, doesn't go away. Now we've moved our charge. Remember, the whole point of resonance is to move this charge around. We've moved it from this carbon onto this nitrogen. If you don't believe me, do the formal charge calculation. So now you have a positive charge on our nitrogen. We've delocalized that positive charge, thus done resonance. So let's look at another resonance hybrid. We're going to draw anytime we have a single bond. And now we want to start thinking about, okay, where are double bonds sometimes? There's only one bond that changes in this one. So sometimes there's no double bond here, and sometimes there is a double bond here. So to show that, again, we do that sort of dashed line. As for our charges, no one atom is carrying a full charge at any given time. Because remember, these are constantly switching back and forth faster than you can even imagine. So it's really like this atom has a partial positive, and this the nitrogen also has a partial positive. Any questions on that? So the other thing that we talked about yesterday that we haven't talked about yet today is determining what is the major resonance contributor. So let's look at our first one. We go through our list. Why does the nitrogen have a positive charge? Good question. So if we go through our formal charge calculation, nitrogen is 5. And now it has 1, 2, 3, 4 bonds. So minus the number of bonds, that would equal positive 1. That's how it gets that positive charge. And again, a good way to check yourself is that conservation of charge idea. Okay, so determining major resonance structure. Here, we have a negative charge either on this or this. If we go back to our kind of list of things we check for, I'm not sure you have the tools to differentiate these yet. So they're both on the same atom. So because they're on the same atom, they have the same electronegativity. These, I should grab my notes from yesterday. We don't have the tools to determine the difference here. Everything has a full octet. That's number 1 on our list. Octet. Then we look at atom. Then we'll look at electronegativity, so on and so forth. So this one we can't really differentiate, so this wouldn't be a type of question on an exam. Or maybe it would be. You have to tell me that they're equally resonance contributors. However, this bottom one does have a clear winner. So take a second, think about which one there would be the major resonance structure. I'm going to go grab those notes from yesterday. Got two people saying it's the right one. So going back to our rules from yesterday, how we determine which is the major resonance structure. There's four steps, remember. Which has the most filled octets? So if we look at this one, a plus charge on a carbon means it is missing electrons. So really, around this carbon, it has two in this bond, two in this bond, and then don't forget the implied hydrogen. Six, that's not a full octet. Where this one, everything has a full octet. So just looking at that first rule tells us this one is the major resonance contributor. And this one would be called the minor. Another example, or talk about a different topic. Little confused with rule one. So major has greatest filled octets. So the look at is full. Yes. So here, make sure I'm understanding the question. So is carbon. So you look at the whole overall molecule. In this case, everything has a full octet here. Again, you have to be comfortable with line angle formula to know that. But this is really a CH3, a CH2, CH2, a nitrogen with 2, 4, 6, 8 electrons around it. This, as we just talked about, 2, 4, 6 because of the bond to the hydrogen. So this is missing its octet. This one was a CH3 full octet. This one, the only thing that kind of changed here is our nitrogen. So 2, 4, 6, 8. Even though it has a positive charge, it still has a full 8 electrons around it. So its octet rule is satisfied. Same thing with this carbon here. Again, you have to remember the implied hydrogen. I'm going to be saying that a lot the next few days. But if we look at that 2, 4, 6 with the implied hydrogen, which you are welcome to write in, that is 8 electrons around that carbon. We have a full octet. Yes, the other rules. That's why I grabbed this. So let's look at an example where. So the other rules, we'll talk about it and then maybe I can come up with an example. So after you look for the most filled octets, which has the most bonds? So if we compare these two in terms of that, this has so many bonds, but this one we gained a pi bond or a double bond. So with that criteria, this would also be the major resonance structure. That just helps support your initial decision. Rule number 3 is a negative charge should be on the most electronegative atom. In this case, we're using a positive charge, so it doesn't really apply. But up here, we would be looking at something like that. We only had hydrogens and carbons. So again, can't really differentiate there. And our last one is keep charges as close to each other as possible. So if I were to give you a relatively complex one where there's positives and negatives, that's when this rule would come into play. I could give an example like that. So let's look at this. This one will be a little bit tricky to make up, but see what I can do. Let's say we have a molecule that looks like this. So this actually won't even get to that fourth rule either. We're going to have a rule that um, gets us to the correct answer a little bit sooner. But with your knowledge, how to draw the arrows. So let me talk about arrows. I don't think I've talked about those yet today. When you're moving electrons, remember the negative charge here, all it represents is a lone pair. So there's a lone pair on that carbon right here. When you're drawing arrows, you use a two-headed arrow, just normal arrow, and you want to move from electron rich to electron deficient. However, we can't just jump over everything in between. We have to kind of move one bond or one atom at a time. So with that in mind, this is our electron rich area. This is our electron deficient area. Try to figure out what the resonance structure would look like. There will be a whole bunch of practice problems posted as well. Working on getting those set today, and class will finish chapter 1, and I plan to post a big sheet of homework problems for you guys to do to get the practice that you need. We gave you a pretty big hint at the start saying, okay, here's our electron rich area, here's our electron deficient area. So for our arrows, we always start at electron rich. We could turn this into a double bond, but that would put 1, 2, 3, there's a hydrogen implied there. That put 4 bonds on this carbon. We can't have more than 4 bonds. So this could move over and become a pi bond there. Now, I know someone's going to ask, why don't we turn that into a lone pair? The answer is you can, but let's look at why we might not want to. So the one possible resonance structure is this. Double bond here, double bond here. Okay, the other possible resonance structure that you may have came up with would look something like this. We have a double bond here, and now we have a negative here and a positive here. That is technically a valid resonance structure, but it's not a very good one. Why is it not very good? So instead of going all the way to another pi bond, you could have put the electrons right there for this bottom one. Because of the charges. Yeah, so it has charges, which typically you want to try to avoid. So thinking about our rules in order, do the arrows have to be the same direction? Not sure what you mean by that. You always draw your arrows from electron rich, or where there are electrons, towards the electron deficient area. So in this case, for them to move properly, yes, they're going to be in the same direction. And that is the case with most two-step kind of resonance things. You push something towards a carbon that already has 4 bonds, then you need to break that extra bond towards something else. So I think someone said it's one-sided because of the charges. So yeah, if we think about our rules here, has the most filled octets. Well, that's not a filled octet, but that is here. So that's one reason why it's not great. 2, has the most number of bonds. This has only one double bond, where this has two double bonds. So again, more evidence that this is a better resonance structure. 3, negative charges are on the most electronegative atom. It's all the same here. If we can minimize charges, that's always the goal. So we can completely get rid of charges, again, supporting this resonance structure, and keep charges as close to each other as possible. So although the charges are very close here, and this is technically a better resonance structure than this one, because of that, it still gets beat out by this one because this one satisfies the first two rules. And remember, it goes from more important to less important. On the correct resonance structures, why did you not include the charges? Good question. Let's take a look here. So how do I want to approach this? The overall, I'm going to do it the simple way, then we'll do it the detailed way. The overall charge of this molecule is what? If we have a positive and a negative, the overall charge of this molecule is actually neutral. So our product should be neutral overall, and it is. Here, positive and negative, overall, this molecule is neutral, but it has point charges or formal charges. So throw some vocab in there for you. So why does this not show any charges? Well, we need to look back to our formal charge formula. For that, I'm going to slow it down a little bit. We're going to draw in our hydrogens. So there, and where was the charge earlier? And there. Okay. So I think you'd all agree with me that this carbon has 4 bonds, and now this carbon has 4 bonds. Carbon with 4 bonds is neutral. You don't believe me? That's fine. Let's look at the formal charge formula. Formal charge of carbon has 4 valence electrons. If it has 4 bonds, we minus 4. That is neutral. So that's why there's no charges being shown on this resonance structure. What other questions do you guys have? Resonance can be tricky, and I promise I will provide lots and lots of practice here, hopefully before the end of the day. So 0 is more stable and preferred for major. Yes. If you can take something, and overall, if something has charges and you can make it not have charges legally, following the rules, that is definitely going to be preferred. Think of, again, the refrigerator example doesn't quite work here, but yes, think of this as being shared. Now we're sharing kind of the weight again in the form of bonds, so that no one atom has to carry a whole charge. The one on the right would be the major one. Yes, this one here would indeed be our major. And I will never have you differentiate between minors. These are both minors. One is better than the other. This one would be a little bit better because the charge separation, but it's still not as good as this one. So both of these, if you just called them minor, I'd be okay with that. What other questions or topics do you guys want to discuss? I can keep going on resonance too. Again, treat this as your time to ask me questions. If you're confused, chances are someone else in the class is confused on that same topic. More resonance. Okay, let's keep it going. So let's look at a hard one. Harder, anyways. Let's do this. We haven't seen a lot of rings yet. I'm going to say this all throughout the semester. Do not let rings scare you. They're not scary. I promise they're not. They're just normal molecules like we've been looking at. So with this structure here, let's see what we can do. There is more than three possible resonance structures here, and there may be problems like this. Um, Once you get more practice, you'll start to see more challenging questions like this one. So here we have our atom, a possible resonance structure. I'll do the first step and then I'll let you guys try the other steps. So here, it may not be super apparent where the electron deficient, electron deficient space is. So we need to think back to induction. Remember the inductive effect, induction arrows, partial charges, all that stuff comes back here. So oxygen is more electronegative than carbon. Because of that, we could draw an induction arrow towards our oxygen. That means oxygen has more electron density around it than our carbon. So we just found our electron deficient area. This carbon has a partial positive indicating it is at least partially electron deficient. So that's where we want to try to move this negative charge. So one way we could do that, and there's a lot of different ways to do this. There's more than one correct answer, as you might say. I'm going to move this to form a double bond here. However, when we form a double bond here, this carbon here has 1, 2, 3. Don't forget the implied hydrogen. It already has 4 bonds. So I'm going to take it and turn it into a lone pair on that carbon. You may have already turned it into a double bond. That's fine as well. I'm taking it slowly, step by step. So let's look at what that would look like. We formed a double bond here. We gained a negative charge here. Our carbonyl is still there, and this is still here. Any questions on how I did that step before I let you try doing some more? I'll give you a hint. There's one more you can do from this space, and there's actually one you can do from here. I'll give you 2 minutes. Try to solve that one out. Okay, I gave you your 2 minutes. I actually waited the full time. All right, so to keep going this way, ooh, that's a different color. That's okay. We could take this lone pair, move it towards, remember, this is the atom that has the partial positive. So that is where we're trying to move these electrons towards. When we move these electrons towards that, that put too many bonds on this carbon, 1, 2, 3, 4. So we need to move electrons up onto our oxygen. When we do that, our oxygen would then take on 2 extra electrons, gaining a negative charge. So that would be a resonance structure. And then down here, we could also take, at the start, we could have taken this negative charge and moved it this way and put the negative charge and took those pi electrons, double bond, and put them right here. And that would have looked like that, that, and that. So there are 4 possible resonance structures for this ion. So vocab, ion, hopefully we know that. An ion is just a positively charged molecule. So my question to you guys, and this is where I'm trying to figure out a way to like be able to get active feedback and live feedback from you guys. That's not the chat. Um, I remember doing like Kahoot things in like high school, middle school, but Kahoot's changed a lot since I was in high school. But something like that would be interesting where you guys can like vote and see what you guys think. So out of these structures, we'll call it A, B, C, and D. Why can't you make a double bond on the other side? You can. I think you're referring to right here. Why can't we put the double bond here? And the answer is you totally can. Um, put it here, move electrons up. It would end up looking the same as this, or close enough to this that I'm not going to consider it. And there's some reasons for that that we haven't talked about yet. But considering A, B, C, and D, going back to our rules, which one would be the major resonance structure? Seeing C. Lots of C's. Great. So it would be C because 1, which has the most filled octets? Well, actually, everything has a filled octet here, so that we can't use that to compare. Which has the most number of bonds? They actually all have the same number of bonds. So 3 pi bonds, the rest are single bonds, 3 pi bonds, 3 pi bonds, 3 pi bonds. So we can't use that. The negative charge on the most electronegative atom. Okay, now we're cooking. The only electronegative atom we have in this molecule is our oxygen. So this would be our major resonance structure. The rest would just be minor. Happy to take more questions that you guys have. Another. Another one. Yeah, let's do it. Another with the ring. Absolutely. So in this case, let's do this. Actually, I'm going to do a little knowledge check as well. Make sure we know how to do our formal charges. There is a formal charge somewhere on this molecule. Where is it and what is it? Don't let the ring scare you. I promise, they're not as scary as it thinks. Partial positive negative works with this. Yeah, absolutely. I will do that as soon as someone tells me where a full charge is on this molecule. On the nitrogen. Thank you, Samantha. On the nitrogen. So what Samantha did was look at what we have here to realize, okay, we're in line angle, so everything that's in line angle is assumed to be full octet, meaning we have hydrogens here. However, the nitrogen at its neutral state likes 3 bonds and 1 lone pair. Nitrogen with 4 bonds is going to have a charge. Maybe they didn't remember exactly what kind of charge, but they recognize that. They could then use the formal charge formula. Valence electrons is 5 minus, oh my God, that is, that's not right. Um, that's okay. We're going to roll with it. No, we can't roll with it. That breaks the octet rule. That should be a 3, not a 4. I apologize. That's on me. So NH3, so 5, oops, back to the pencil, minus the number of bonds, minus the number of lone pairs. Wait, there are no lone pairs there. So 5 minus 4 is a positive 1. It would be positively charged, yes. So remember, again, if you try to think through these, that can help sometimes too. If nitrogen in its neutral state doesn't mind sharing 3 lone pair in the form of bonds and holding on to one for itself, we're now forcing nitrogen to share its lone pair. It doesn't want to do that. That means it's sharing electrons it doesn't want to share because electrons carry a negative charge. That's going to leave a positive charge on our nitrogen. In this case, partial charges don't really work. Maybe on the next one, we'll get a better example of how to do the partial positive and negative again, but it has to do with electronegativity. So here is our starting compound. I'm looking for at least 2 resonance structures. How about that? I won't even make you do all of them. So remember, we start from electron rich to electron deficient. And remember what a plus charge means. I'll give you guys 2 minutes to try to figure this out. Maybe a little bit less. How often do you have recitation quizzes? When I taught over the summer, there were 4 of them. I'd like to make them a little bit more common this time around, but I don't have an answer for you, so I apologize for that. I'm still deciding on how I want to administer them and how frequent they're going to be. What I'd really like to do is 1 per chapter, but I want to figure out how I could make that work. For some weeks, we'll only get through 2 chapters. Some weeks we'll get through 4 chapters. It just depends. I don't want to be bombarding you with a whole bunch of quizzes. I know this class is a lot, so I'm not trying to make it harder than it already is. All right, give you your 2 minutes. Let's look at it. So in this case, we have a positive charge. We will never, ever, ever, ever draw an arrow starting from a positive charge. Not going to happen. We want to start from electron rich to electron deficient. So this isn't going to work. Hold on a second. Hold on a second. This isn't going to work. All right. So it's not going to work. And I want you guys to tell me why. If we try to push this lone pair up towards this nitrogen, what we would get out is something that looks like this. I'm telling you that that is not, although you followed the rules here in terms of arrow pushing, that is not a valid resonance structure. Yes, we have broken the octet rule. And something you always need to remember is that we cannot break the octet rule. So these are not resonance structures, and there's actually no resonance stability for that positive charge. So let me give you one which actually can do resonance. I apologize for that. But that's okay because that's something I could put on an exam and you have to tell me there is no resonance stability. Let's look at NH2. This one we can also talk about partial positives and negatives. Okay. So, starting with this molecule, which will actually work, we want to figure out where electron-rich place is and where electron-deficient place is. So, in terms of electronegative atoms, which is the most electronegative atom of this molecule? If I go over, just tell me. Have I gone over? I don't remember when this ends. Nitrogen, yes. That's not where my phone is. Yes, our nitrogen is 1010. Okay, great. So we'll wrap up. This will be our last example. Nitrogen is our most electronegative atom. So this actually has a partial negative charge. Because this has a partial negative charge, this bond, what would we call this bond? Is it polar or non-polar? It's polar. Very good. Because this carbon that is attached to that electronegative atom has a partial positive. Because this has more electron density around it, where did it take it from? It took it from this carbon. So we draw an induction arrow starting at the positive charge. So we draw a plus sign at that partial positive towards your partial negative. From there, we know this carbon is the one that really wants the electrons. So, although I've kind of already drawn a whole bunch here, everyone say hello to my cat Claire as a goodbye thing as we celebrate our last practice problem. This, let me change colors at least, can come down to form a pi bond and move this pi bond to become a lone pair. So 1, 2, 3, 4, 5, 6. Now here would be a negative charge. We still have our other pi bonds intact, and this has a positive charge. So, yes, so partial positive negatives typically are most important, or where we really see them is in overall neutral molecules, because a full positive or negative would just overpower a partial, so it's not as important. So here, now we have this. There's charges here. We went from a non-charged molecule to a charged molecule. I'll let you guys on your own time figure out why those charges are there using the formal charge calculation. But last thing I want to know before I let you guys go is what is our major resonance structure here? 1 or 2? 1. Absolutely. 1 has no charge, no overall formal charge. where 2 has charges. Neutral is always more stable, or the major resonance structure over something that has a charge. So this would be our major. This would be our minor. Thank you guys for attending recitation today. Hopefully you found this helpful. Lots of practice problems to come. Go take a 20-minute break before you have to listen to me spiel for another long time. I will see you guys soon.